Dr. Weinstein, let's talk about tsunamis. We recently spoke to a tsunami survivor, and so we learned all about his experience and how traumatizing it was. But I want to hear about tsunamis themselves. I think there's a lot misunderstood about them, and things have come a long way, too, as far as the warning system, from what I understand over the past couple of decades. So can you tell me what your position is and where you work?
Well, I am the science officer for the Pacific Tsunami Warning Center, and the Pacific Tsunami Warning Center is based on Ford Island in the middle of Pearl Harbor.
Okay, so you live in Hawaii.
I live in Hawaii, yes.
How long has the Pacific Tsunami Warning Center been there?
Well, the Tsunami Warning Center has been in Hawaii since 1949. The tsunami warning system got started in Hawaii following the 1946 earthquake in Alaska that generated a tsunami that caused over 150 fatalities in the then territory of Hawaii. So the tsunami warning system became operational in 1949. And following the 1960 Chile earthquakes and 1964 Alaska earthquake, which also generated destructive tsunamis, a Pacific-wide tsunami warning system was created in 1965, and the center in Hawaii became the center for the Pacific Basin Tsunami Warning System, now known as the PTWS, just the Pacific Tsunami Warning System.
And you guys fall under the National Weather Service, correct?
That's right. The tsunami program is within the National Weather Service.
Okay, so it's a little confusing. And then also you have a specific territory, right? So sometimes warnings come out of different offices depending on where they are.
Yes, there are what we call regional tsunami service providers, for example. Now, most of, if not all the countries in the Pacific Basin have what we call a national tsunami warning system. But there are different areas where, for example, there are what we would call tsunami service providers. For example, in the Northwest Pacific, Japan operates the Northwest Pacific Tsunami Warning System, and in the South China Sea, China operates the South China Sea Tsunami Warning System, and perhaps later in 2025, Nicaragua will operate a regional center for Central America. The National Tsunami Warning Center in Palmer, Alaska, they provide warnings for all the coastlines of North America.
Okay, gotcha, I think.
And we have basin-wide responsibility. So basically what happens if, let's say, there's an earthquake in the South China Sea, China will issue whatever products they deem required for that event, and then PTWC will follow suit using their parameters. But then following that, we will use our procedures subsequently. If the earthquake occurs outside those regions, like if there's a great earthquake off the coast of Ecuador or something like that, then we will provide the initial tsunami message products for that earthquake.
Okay, let's go back to tsunami basics. For those who don't understand, and I think it's even confusing to people who do kind of understand how tsunamis work, what causes a tsunami? And it's not all earthquakes, right? Can you give me some basics here on tsunami science and how they happen?
Well, basically, any phenomena that causes a sudden displacement of the ocean column can generate a tsunami. So approximately 80% of the known destructive tsunamis are actually generated by earthquakes. Imagine, so after the Japan 2011 earthquake, imagine that you've had a prism of water that was about 350 kilometers long, 75 to 100 kilometers wide, and perhaps as much as 10 kilometers thick. And you now picked up this whole prism by like 10 to 15 meters. As you might imagine, that's a lot of water in there, and the amount of energy needed to pick and displace all that water is quite enormous. And so in the immediate aftermath of the earthquake, you've created this mound of water, and water doesn't hold itself, so it collapses. And so all the energy that was used to pick up this water is then released in a series of traveling waves that we call tsunamis. And that's why they can be so very destructive.
So you said 80% of tsunamis are caused by earthquakes. What are the other 20% caused by?
Well, landslides. You can have landslides falling into the ocean or what we call submarine landslides. Sometimes these happen by themselves or sometimes they're triggered by earthquakes. And another mechanism for generating earthquakes as well, this occurred relatively recently, volcanic explosions. So, yeah, there are different ways we can generate tsunamis.
You said submarine landslide?
Right.
What
Yeah,
is that?
beneath the ocean.
Okay.
Yeah. Yeah, I don't mean submarines. I mean,
Like, what are they doing?
yeah, submarine just means below the ocean surface.
And I've heard of meteos tsunamis.
That's
Am I
right,
saying that
meteos.
right? So
Yes.
are those ever like really destructive like regular tsunamis, or are they a whole different class?
Well, they can produce hazardous waves. In general, no, they're not as destructive as tsunamis caused by great earthquakes. But back in, I think it was 2013, a meteor tsunami did strike the east coast of the United States and hurt like a dozen people or so. So they can be destructive, they can be hazardous, and meteor tsunamis don't just occur in the oceans, but they can also occur in the Great Lakes in the United States. And there is some consideration about developing a meteor tsunami warning system for the Great Lakes in the U.S.
Interesting. Okay, so let's talk about what makes like the kind of perfect storm of a tsunami. What kind of earthquake? How deep? How far from land? Is there like an equation for a really destructive tsunami?
Well, basically, the kinds of earthquakes are what we call thrust earthquakes. This is where the motion along the fault is vertical. So, for example, the San Andreas Fault in California, that's where motion along the fault is horizontal. And the recent earthquake off the coast of California was also due to horizontal motion. In general, those aren't particularly efficient at generating earthquakes because most of the ground motion is horizontal, and therefore you're not really displacing the water column.
So like the plates are going like this instead of like
That's
this?
right.
Okay.
That's right. And at a thrust earthquake, the plates are either moving up or down, displacing the water vertically. So
Do they
that's more
stay
efficient
up?
at generating.
Do the plates stay up? Like, is that land permanently higher?
For the time being, but as long as subduction keeps going, then eventually it gets pulled back down again.
Okay,
So
so
that's kind of like a cycle.
I was curious,
Pops up.
like if sea level rise, if there's like a change in sea level because of that. I guess it would just be
Yes.
temporary. There is?
Yes.
Wow.
Yes.
And
So
it's
after
measured?
the land rebounds, well, actually, it's not a sea level rise; it's a sea level drop.
Okay,
So
interesting.
yes, that
Okay, so let's talk about the 2004 Indian Ocean tsunami. This is one that obviously stands out to a lot of people. It's been 20 years since this happened, but this one is the one I think of as like just ridiculous how many people died. I mean, we're talking 250,000 people, so many countries affected. What about that particular tsunami made it so impactful to so many people and then also so deadly to so many people?
Well, it was generated by perhaps the third largest instrumentally recorded earthquake.
So number one, big earthquake was the starting
It was
point.
huge, yes. But the main problem was that there was really no functioning tsunami warning system in the Indian Ocean basin. At that time, only the Pacific Basin had a tsunami warning system. There was also very little seismic information and sea level information coming from that area of the world. So, I mean, the Pacific Tsunami Warning Center, that they did what it could. But the world learned a very hard lesson that a tsunami warning system can't be stood up in a few hours. It takes years. And I think it wasn't really till around 2013. Well, following the Sumatra earthquake, we became the interim Tsunami Warning Center for the Indian Ocean Basin. So that started in like 2005 and continued till around 2013 when we passed that responsibility off to the three tsunami service providers in the Indian Ocean. One is in Jakarta, another Hyderabad, India, and the third is in Melbourne, Australia. So they became operational, I think, in late 2013.
As a result of
As
this
a
event.
result of that. In fact, it was a wake-up call pretty much for the rest of the world because, well, yeah, it's not just the Pacific Basin that has destructive earthquakes and tsunamis. The Indian Ocean has them, the Caribbean Sea has them, so there is a tsunami warning system in the Caribbean Sea. The PTWC is the warning center for the Caribbean Sea. And tsunamis do happen in the Mediterranean and North Atlantic. So there is a North Atlantic and Mediterranean tsunami warning system that actually has 5 tsunami service providers, one in Turkey, Greece, Portugal, France, and Italy.
Are there any holes in the world when it comes to tsunami warning? And if so, where are they?
Yeah, I think the South Atlantic, we don't really have a tsunami warning system for the South Atlantic. And the need for one was highlighted by the 2021 South Sandwich Islands earthquake sequence, which did generate a tsunami that produced hazardous waves in South Africa, for example.
Okay, so first, giant earthquake, no tsunami warning system. And then something else I noticed when watching, because I've watched a lot of videos of, tourists and survivors, and a lot of them said the same thing in the videos over and over again. What is that? What is that? Even people walking.
Lack of tsunami awareness. Yes.
Right. So people not knowing what it was and then also how it works. And the survivor I spoke to said he was shocked at the number of people he saw walking out when the water receded. So can you tell me about what happens there, why the water recedes before a tsunami? And does it always?
No. It depends on where you are relative to where, the tsunami was generated and how it was generated. So what happens is sometimes the trough of a tsunami arrives first. And so that's a depression of the sea surface. So as the trough arrives to the seashore, then the water along the coast starts draining into that trough. And so you see the recession of the ocean. And so all of a sudden you see a section of the seafloor that you've never seen before because the ocean has receded. And unfortunately, a lot of people were like, this is interesting. And they went out to take a look.
Yeah, he said fish were flopping around in the sand.
That's right. Yeah, they could be left to us if the ocean recedes quick enough. Of course, then at some point, the crest of the wave arrives. And then that's when the inundation happens and the destruction. So that's an important warning sign. If you're on the coastline and you see the water start receding in a kind of like unnatural way, run inland and uphill. Don't wait for the tsunami warning.
What typically is the time period once you see that?
Kind of depends, but once you see the water receding, you may have anywhere from 5 minutes to 20 or 25 minutes. Yeah, it sort of depends on how big the tsunami is. The bigger the tsunami, typically, well, for an ocean crossing tsunami, they will have periods anywhere from like 30 minutes to an hour. In other words, the period is the time elapsed between successive arrival of let's say the crest of the wave. So if you see the trough, if you see the water receding, then you know the trough has arrived. And then the crest of the wave will approach about a half a period later. So that could be anywhere for an ocean crossing tsunami, that could be anywhere from 10 minutes to 30 minutes.
How fast can they travel? So if there's an earthquake, hundreds of miles away, how long will it take for that tsunami to reach a shoreline?
Well, in deep water, a tsunami can travel at the speed of a jetliner. The deeper the water, the faster the tsunami travels. So, for example, if you left Narita Airport at the same time the 2011 earthquake struck Japan, you'd probably arrive in Honolulu Airport, within, 30 minutes to 45 minutes of when the tsunami would arrive. Now, the thing is, even though that's pretty scary, what the tsunami is traveling at the speed of a jetliner in open ocean, the fact of the matter is tsunamis are not hazardous in the open ocean. They're not hazardous in deep water. That's because the it has to do again with the period of the tsunami and the amplitude of the tsunami in deep water. Even for a tsunami like the destructive 2004 tsunami, maybe its amplitude in deep water, that is from normal sea level to the highest point of the wave, was maybe about a meter, around a little more than 3 feet. So if you were in an ocean liner while the Sumatra tsunami was passing under you, your ship would have gone up and down by a couple of meters over the course of 45 minutes. You would not have felt it. You would not have felt anything.
That's wild.
Yeah. Now what happens is
there were people scuba diving near the coastline in Thailand, and they barely felt anything as well.
You mean as far as the earthquake?
No, as far as the tsunami, like they were underwater scuba diving out in the ocean, and they said it passed over them. They didn't even notice it.
Well, if they were in deep enough water, they might have, in some locations, they could have got lucky. But so basically, again, in very deep water, the wave amplitude of the tsunami is not particularly that large, and the period is so long that the vertical motion, up and down motion of the ship due to the wave is too subtle for you to detect. However, as I mentioned earlier, the speed at which a tsunami travels depends on the ocean thickness. It's a simple formula, square root GH, where G is the acceleration of gravity and H is the water thickness. The depth of the water column. So as you get into shallow water, the tsunami has to slow down. So basically what happens is let's say this hand is the leading edge of the tsunami wave and this hand is the trailing edge of one of the tsunami waves. So as the tsunami propagates into shallow water, it has to slow down. So what that means is that the wavelength of the wave decreases, but nonetheless, energy is conserved. So all that energy that was contained within the wave that had, let's say, a wavelength of several hundred kilometers, well, it's now shrunk to, because it's now in shallow water, that wavelength has now shrunk to maybe, a few kilometers. So what happens with all that energy? Well, the amplitude of the wave becomes much greater. So what is not hazardous in deep water can become horribly destructive as it gets into shallow water. And so
makes sense.
That's why tsunamis become so destructive along the coastline.
Okay, so take me through a tsunami warning, kind of from start to finish, and what you guys are doing at the Tsunami Warning Center, and then how you come up with, do we warn, do we not warn? What's the warning time? How does all of that work?
Well, the tsunami warning systems are really geared for tsunamis generated by earthquakes. That doesn't mean we don't pay attention to tsunamis generated by other means. But the thing is, tsunamis generated by earthquakes are kind of like the easiest to detect and warn for. Because seismic waves, because as fast as the tsunami travels, seismic waves are much faster. They can travel several miles a second. And so if there's a big earthquake, we're going to know about that earthquake within a few minutes. So we'll have it located. We will have an estimate of the magnitude of the earthquake. And depending on that information, we will issue our initial message product. And depending on the magnitude, depth, and location. So, for example, for the recent event that occurred off the coast of San Francisco, the criteria for the National Tsunami Warning Center basically is any earthquake above 7.0, they're going to put a certain section of the coastline within a warning. But depending on how big the earthquake is, then the greater the earthquake, the larger section of the coastline that will be placed in a warning. And that was done within a few minutes. And then after that, we will continue to evaluate the earthquake, refine the location, come up with better estimates of the magnitude, and then we're going to keep track of what's happening in the ocean. How big was this? What was the amplitude of the tsunami recorded on the darts? What was the amplitude of the tsunami recorded on coastal sea level stations?
What's the DART?
Okay, the darts, they are bottom pressure sensors. They are maintained by the National Data Buoy Center. And it's very, very good information to have what are the characteristics of the tsunami in very deep water. And if we generate tsunami forecasts, we can use that information to validate the forecast or tell us we're under forecasting or over forecasting, etc. Likewise, we can also generate a forecast for what we see along the coastline. However, the forecasting what a tsunami is going to be like along the coastline is a lot more complicated than forecasting what it's going to be in deep water, because the topography and bathymetry along the coastline is very complicated. So you need much more sophisticated modeling. But nonetheless, if we have an idea of what's going on in the deep water, that'll tell us, oh, is this going to be a destructive tsunami as it propagates across the ocean? Those kinds of things. And the coastal sea level stations, they give us the facts on the ground. Okay, what actually is happening on the coastline? So after that warning went out and no hazardous tsunami was observed. I mean, tsunami did strike California, like in Arena Cove, but it was small and non-destructive, fortunately. And so the tsunami warning that was put in effect was canceled.
Yeah, pretty quickly. I noticed it was. Yeah. Do you think there are any spots that perhaps are most vulnerable to a large destructive tsunami? You mentioned how the West Coast, the way the faults are situated, it's not as big of a risk of a big tsunami. Are there situations that are at greater risk, though?
Well, yeah. Basically, what geophysicists call subduction zones. These are the areas where the Earth's plate is moving back into the Earth's interior. And the Pacific Rim is basically subduction zones for the most part. Japan, you have the Japan Trench, subduction zone, Chile-Peru Trench. You have a subduction zone off the coast of New Zealand, etc., off the coast of in front of the Aleutians, just to the south of the Aleutians, for example, Kamchatka, etc. Most of the Pacific Rim is a subduction zone. And a subduction zone is what I like to call the triple threat. Because at a subduction zone, you can have great earthquakes, you will have volcanoes, and you will have tsunamis. And for the United States, a particular concern is off the northwest coast of the United States and Canada. This is known as the Cascadia subduction zone. And back in 1700, there was a great earthquake there that we know from history produced a destructive tsunami in Japan. And at some point, this is going to happen again.
I think, many people don't know about the forecasting strength or weaknesses when it comes to tsunamis, and don't know that earthquakes can't be forecasted. Do you think we'll ever get to that point where we can forecast an earthquake, therefore increasing this warning time of tsunami?
Don't think so. Let me put it to you this way. The idea that in the year 2030, on April 14th at 10 in the morning, there's going to be a 9.1 in the Chile Trench. That's not happening. I think the best we can do, is and there's still some active research on this. I don't want to get into the details. It's not something I'm particularly spend a lot of time on. The hope is that at some point we will uncover certain phenomenon that indicate that a great earthquake might be coming within a few minutes or so. So I think the best we can do is give a bit of a heads up. Earthquake early warning systems, while they don't give you a heads up in advance of the great earthquake. Once a great earthquake has been detected, the earthquake early warning system can then tell you that a great earthquake occurred. And you may, depending on how far away you are from the epicenter or so, you may have anywhere from a few seconds to several tens of seconds to take cover and hold. So at least that'll give you a little bit of warning. But as far as some sort of warning prior to a great earthquake, that's going to take some research, but it's not going to be done like for hurricane warnings. We have like days in advance,
12 days.
Yeah, that's not going to happen. That's not going to happen for earthquakes. Wish it could, but no, I don't see that happening.
So if there was an early warning or if there was a tsunami warning, is that something like a weather warning that would pop up on our phone? Is it a wireless emergency alert?
Yes, yeah, the earthquake early warnings and the tsunami warnings will pop up on the cell. Yeah,
Is
a
there
wireless emergency alert.
is there anything that you often hear as a misconception when it comes to tsunamis or earthquakes that the public really gets wrong?
Well, that's a good question.
Or even something you see in movies where you're like, ugh.
Oh, well, yeah, glad you brought that up. Yeah. I remember a movie that I saw when I was a kid, The Poseidon Adventure.
Okay.
Yeah, you don't know that one, huh?
No.
Trying to remember the actor's name, but anyway, who was the captain of the ship. And basically, in the Poseidon Adventure was a disaster movie in the early 70s. And you had this cruise ship that basically got knocked over by a tsunami in the middle of the ocean.
Okay.
Okay, that's not going to happen.
Right. Little bop.
Yeah, little bump. The tsunami will propagate. The ship will go up and down over the course of tens of minutes. It's not going to get wrecked. Not going to get knocked over by the tsunami wave in the middle of the ocean.
Gotcha.
So yeah, the other thing is a tsunami is also kind of like a scientific term. So a tsunami wave doesn't have to be big. Scientists will still call it a tsunami if it's a wave that's generated by displacement due to the sea column. So the tsunami that arrived, let's say in Arena Cove in California, due to the recent off the coast of California quake, it was, I don't know, like 14 to 15 centimeters, maybe trough to peak. I mean, that's small, but it's still a tsunami,
Is it a
just not
tsunami
destructive.
if something falls from the sky or space and
Well,
displaces water?
a meteorite can generate a tsunami. That's another mechanism.
Okay.
Yeah, I think that was also in a science fiction movie.
Well, the
Meteorite
reason I
generated
ask is
tsunami.
I interviewed an astronaut recently, and he was talking about them bringing down the International Space Station and how they're just going to crash it into the ocean. So that seems like it would generate a wave, right?
Well, yeah, if you're nearby, but it's not going to displace the water column proper and generate a tsunami. It'll make a mess, but it's not going to generate anything that you'll detect on a coastal sea level station unless
So it's more just like somebody doing a
lands
cannonball
relatively
into a
close to the
pool.
coast. But a
I think they're
meteorite,
hoping no.
a big meteorite, yeah, a little bit of a different story.
Right, right. Gotcha. What's the future of tsunami warning look like? What are some goals for the next, I'd say maybe couple of decades when it comes to tsunami warning?
Well, we want to try and get better and better. We want to try and be able to come up with more accurate tsunami forecasts, better characterize great earthquakes, do it quicker and sooner. And also we want to be able to, also there's more emphasis now on us dealing with tsunamis generated by non-seismic sources, like volcanoes, for example. So one of the problems with, for example, the Hunga Tonga explosion was how do we quickly assess the energy release of this explosion? And science at that time didn't really have a way to do it quickly, but that's changed. So, for example, when I went to an SSA meeting a few months after the Hunga Tonga explosion, that's a meeting of the Seismological Society of America. There were a number of talks regarding what transpired in Hunga Tonga. And at that time, estimates of the energy yield of the explosion ranged from like 30 to 60 megatons of TNT. It was the equivalent of detonating 30 to 60 megatons of TNT. Well, then a few months later, it was, okay, maybe it's like 60 megatons to 90 megatons. And now, okay, yeah, it seems to be on par with Krakatoa back in the 1880s, anywhere from 150 to 200. Mind-blowing. There have been studies using what's known as infrasound. This is like low-frequency sound that you can't hear, but nonetheless, it can be detected by instruments. And based on analysis of infrasound, if we were able to do this back at Hunga Tonga using infrasound, we might have been able to roughly estimate the size of the explosion within like 20 to 30 minutes using infrasound. So that's one advantage. We are also looking at using GNSS. GPS tells us how the ground actually was displaced. Until fairly recently, seismologists would just tease how much the ground was displaced by analyzing the seismic waves generated by the earthquake. But now we can get some information from how much the ground was displaced due to GPS. This is also known as GNS, which stands for Geodetic Navigation Satellite System, I think. That's what it's called. And we're also looking at techniques that combine seismographs with GNSS. I don't want to get too far into it, but what that allows us to do is perhaps rapidly estimate the size of even the greatest earthquakes, like the Japan earthquake, in 3 minutes, in 3 to 3.5 minutes. That tells us, okay, we need to get out a warning for like this entire coastline to start. And as we get the particulars later, then we can generate a forecast. Using GNSS, that helps us determine what was displacement along the fault. And if we get more information about the displacement along the fault, then we can generate more accurate forecasts, things like that. So also we have to really realize that tsunamis are examples of air-sea interaction, because tsunamis have relatively long periods as the tsunami propagates across the ocean. Even though like the amplitude isn't that great, it's still a long enough period, still a long enough wavelength. The wavelength of the tsunami is many times the thickness of the atmosphere. So as the tsunami is propagating across the ocean, it's moving the atmosphere up and down. And that affects things like GPS transmissions, known as total electron content.
Whoa, I didn't even think about that.
Yeah,
That's wild.
And it also affects the ionospheric afterglow. So the ionosphere is currently always sending radiation back into space. And as a wave propagates through it, that changes the intensity of that radiation. So in the future, ionospheric observations may become important in tsunami forecasting.
Interesting.
Yeah, that's probably a bit ways down the line. But if you're saying like over the next 20 years, yeah, I'd be surprised if that doesn't happen over the next 20 years when we incorporate ionospheric observations. Now, that won't help for like locally destructive tsunamis, tsunamis generated by earthquakes in the sevens, for example, because those tsunamis won't have, let's say, a long enough wavelength or propagate far enough to cause much displacement of the atmosphere. But for the ocean crossing destructive tsunamis like Tohoku, like Sumatra, like Chile, etc., yeah, those will help. That information.
What about education and outreach? As simple as like people going on vacation to a place that might be prone to it, like in Hawaii. I've never been to Hawaii. Is there like educational resources, kind of in the way that like when you go to a tornado prone area, it says tornado shelter here.
Right. Yeah. If you come to Hawaii, you'll see on the beaches of Hawaii, it'll tell you are entering a tsunami hazard zone. It would also give you some ideas of how do you leave? What's the quickest route out of here?
Yeah.
So there'll be some of that information. I think I'm not 100% sure, but I think the hotels do provide some information on that. Prior to 2004, there was a little bit of resistance in that regard. Oh, we don't want to scare people. But but following the Sumatra earthquake and tsunami, okay, people understand that. I mean, that was one of the major things. That tsunami really profoundly increased public awareness of the tsunami hazard and risk, because there was so much video made available of what that tsunami did that people got the message. When I first came to Hawaii as a postdoc at the University of Hawaii, and I think it was 1994, there was an earthquake in the Kuril Islands, and a tsunami warning was issued to the state of Hawaii. It was issued in the morning. The sirens went off in the morning, woke me up. I was living in Waikiki at the time. The tsunami wasn't going to get here for a few more hours, but I got in my car and drove to, and along with all my colleagues, we were watching TV, and the news media were interviewing the local tsunami expert, Professor Gerard Fryer, talking about tsunamis. And in the background, they had a screenshot of the North Shore of Hawaii and all these surfers waiting for the wave to arrive. And I was like, are these people crazy? Because if a destructive tsunami did arrive, most of them would have been drowned.
Mm-hmm.
Tsunamis aren't surfing waves; they are drowning waves. And I was just like dumbfounded. Well, almost 30 years later, 20 years later, excuse me, back in 2011, when we issued the tsunami warning for the tsunami generated by the great Tohoku earthquake in 2011. And there was nobody on the North Shore waiting to surf the waves. Everybody got the message. There was so much video of coming out of Sumatra, Thailand, all the places in the Indian Ocean that, yeah, it's not the smart thing to stay on the coastline during a tsunami warning. And the public got the message. And today they like, okay, yeah, if there's a tsunami coming, yeah, we definitely want to know about it. So I think the public attitude has definitely changed following the 2000.
Yeah, and if you think about just like the kind of social media between then and now over the past 20 years, what's changed there, and YouTube, and just the availability of video, not just the fact that it was taken, but the fact that people can post it and share it.
Right. So people now can take a look and see for themselves. Oh my God, this is what a destructive tsunami looks like.
Well, Stuart, I don't have anything else. Is there anything else you want to share about tsunami education to the general public, or anything else you want people to know?
Yeah, just a couple of things. Safety signs. So we already talked about if you see the ocean receding unnaturally, that's a heads up that a tsunami is coming. But there are actually other warning signs too. For example, if you're on the coastline near the ocean, etc., and you feel strong ground shaking, like you have a little trouble maintaining your balance, don't wait for the tsunami warning. Don't wait for the tsunami to get there. Inland and uphill as soon as possible. Likewise, if you feel kind of like gentle shaking or whatever, but it lasts for like tens of seconds, it could mean one of two things. One, that we're dealing with a slow or what's called a tsunami earthquake, or it could mean that there's a great earthquake maybe a couple 100 miles away or further. Don't wait for the warning. Just inland and uphill. The worst that happens is you took a walk for nothing. The best that happens is you just saved yourself. So there are some natural warning signs. Take heed of those. If you're in a coastal area and you're in a seismically active area, keep those in mind.
Cool. Stuart, anything else you want to share?
I think that's about it. It's been a pleasure.
Yeah, same. Thank you so much. Lots of great information here. And I think there's still a lot for the general public to learn about this too.